Let me give you a problem to consider, and then we're going to talk about it. Let's say that you go to the beach and you come home from the beach and you want to hang your wetsuit up to dry, and you're going to hang it on a wire that you have in your dorm room. Okay? So let's see if we can just draw a very simple picture of what this looks like, right? Let's draw a hanger, and now we have a wetsuit hanging on it. And then we're going to hang it from a wire. So it looks something like that. You got ridiculously skinny arms on your wetsuit for whatever reason. We know that there's got to be some tension T in the wire to hold up the wetsuit. Let's say we want to do the following experiment. We want to calculate what tension T to keep the wire perfectly horizontal. In other words, no sag in the wire. Okay? If we want that wire to be perfectly horizontal, what would that look like? It would look like this. Here's our hanger. Here's our wetsuit. The wire would be perfectly horizontal, like that. And there would be tension T in that wire. What tension T would it take to keep that wire perfectly horizontal? All right, let's think about it. Let's say that the wetsuit has mass M. What's a guess? Let's take a guess. This is a good idea in physics. Just guess at some possible solutions, and then when we're all done, we'll see if any of our guesses were right, and this allows you to get in touch with your intuition. So what's a good guess? What do you guys think? Somebody shout out a guess. Okay, what'd you say? The mass is M. So how about mg, right? Why not? We know as the mass gets bigger, that tension T must get bigger. So maybe mg. More than mg. Okay. How much more than mg? Twice. Okay, that's a good guess. There's also two wires though, so maybe the tension in each wire could be less. So how about mg over 2? How about 0? No tension in the wire. Any other guesses? Say that again, but put your mic on so the people at home can hear you. And what's your name? Keaton? Okay, Keaton with allergies, what did you have to say about this one?
I was saying, since there's a mass on the string, it can't be perfectly horizontal.
It can't be perfectly horizontal. So what would the tension be if it can't be perfectly horizontal?
Really, really big.
Really, really big. What's really, really big?
MG.
Okay. Well, that would be getting us into the wrong units. So what if we just said, I don't know, 1,000 mg? That's really big, right? Okay, here's some decent guesses. Any of those that we can get rid of? 0. That doesn't make any sense, right? No way can it be 0. Anything else we can get rid of? mg and mg over 2. I'm not sure we really want to get rid of those yet because we kind of like mg's. So why don't we just hang on to the rest of them for now and we'll see how it goes. Okay, how do we do this problem? The way we do this problem is, first off, we simplify it quite a bit, right? Let's take that picture right here and let's simplify it. So, wire, mass M, wire, that's basically this picture right here. Let's approach it from the point of view, we're going to call that theta, and then we will look at the limits later on. So if that's theta, this is theta, this is also theta, and this is also theta. And then we have tension T in the wires. Okay, so we solve it this way generally, and then we can look at the limits as theta goes to 0. All right, there's our picture. We got to do the free body diagram. So let's draw the box as a dot. What are the forces that are acting on the box? The first one we love, gravity. And then we have tension T going up like that, and we have tension T going up like that. That looks pretty good, except it's not all in sort of X, Y, beautiful Cartesian coordinate space. And so let's redraw this as something that has components in it. So let's draw it like this. mg is still down, but now there is some component of tension to the right. There is some component of tension to the left. There is some component of tension up. And there is some component of tension up. So this is an equivalent picture if we can figure out what these different components are. So this one right here is going to be either T sine theta or T cosine theta. Which one should it be? Cosine. Why? Because this angle right here was theta. So T cosine theta to the right, T cosine theta to the left. And that means that these vertical ones have to be sine. T sine theta, T sine theta. Perfect. That looks like a great free body diagram. And now we can go to sum of the forces. In the x direction, it's not really going to tell us very much, right? Because we have T cosine theta to the right, but we have T cosine theta to the left, and all of that is going to equal 0 because the thing's at rest, and that's good. 0 does equal 0. The y equation, hopefully, will tell us a little bit more. What do I have? I have 2 T sine theta going up, and I have 1 mg going down. And all of that is equal to the mass times the acceleration in the y direction, but if it's just hanging there, that's 0. And so now we get a solution for T. T is mg over 2 sine theta. Let's put a box around that. So we got an answer. Let's make sure that it makes sense. Do the units make sense? Tension is a force. mg is a force. Sine theta is unitless. So the units do work out. Let's look at the limits. And to start with, let's say that the thing is hanging straight down. So if it's hanging straight down, what is theta? What would theta be if it's hanging straight down? Theta would be 90 degrees. What's the sine of 90 degrees? 1. So what would the tension be? It would be mg over 2. And that makes sense, right? if the two wires are going to hold the weight, each wire has to hold half of it. No problem. Now, the original question was, what if it's horizontal? If we have a horizontal wire, what is theta? What's theta in this case? Okay. It's when this wire goes to the horizontal, which means theta goes to 0. You could plug in 180 too, and you get the same answer, but theta equals 0 is what we're looking for. What's the sign of 0? Sine of 0 is 0. If sine of 90 was 1, then sine of 0 had better be 0. So what is the tension? It is mg over 2 sine theta, which becomes mg over 0. What's mg over 0? It's infinite, right? Anything over 0 means that you are approaching infinity. So it can't be done. Our guess of it being really, really big was right, but it's not 1,000 mg, it's not 10,000 mg, it's infinity. Can't be done. And this is kind of weird, right? I mean, it seems like I could just pull on this wire really hard and get it to be horizontal. And I could put just a little tiny mass on it and it would stay horizontal, but that's not what happens. No matter what the wire is made of, no matter how strong you pull on it, what the tension is, you can't get it perfectly horizontal. And this is good to remember when you're an engineer, right? When you are building a bridge and you think, oh, I'm going to string this cable and it's going to stay perfectly horizontal. No, as soon as you put some mass on it, it starts to sag. And in fact, you don't even have to put mass on it because the cable itself has mass in it. And so the cable will start to sag. And this is part of the point for you engineers. Everything bends, everything sags when you apply forces to it, things move. So when you're engineering a building or an airplane or a suspension bridge, keep this in mind. Everything is going to sag. You can't keep it perfectly horizontal. Just kind of weird, right? That's the way it is.